The first element that I want to talk about is what can users do to help them pass or help them meet compliance when they're working on their project. When should they really be looking at the energy analysis side of things, and what should they be looking at to help influence their design decisions really from the early stages? Okay. Now, the first thing I want to talk about is really sort of understanding the notional building and understanding how the target emission rate is going to be sort of calculated. Now, in 2010 and 2013, the calculation method for the target emission rating changed quite drastically from 2006. Under the previous regulation method, back in 2006, you had a notional building which was representative of 2002, or a building that would have passed 2002 regulations. Then in order to improve upon that, it had a number of weighting factors applied to it. So you had improvement factor and a low zero carbon factor. So under 2006, you generally had a target emission rate that was weighted about 28%, that's our ballpark, lower than your notional building. Now, when the 2010 sort of consultation came out, there were two proposed approaches given in the consultation. One was to implement an aggregate reduction of 25%, and the other was to implement a fixed reduction. Now, with the fixed reduction, it would have carried on in much the same sort of way as it was in 2006. You'd have the same notional building built to 2006 standards, but with that, 2002 standards, but then with an even further improvement factor applied onto it. Now, the advantage of that was that you would have a fairly predictable target reduction. So prior to the 2010 regs coming in, as designers were working on their projects, they would at least have a good ballpark understanding as to whereabouts their emissions rating were going to lie. Now, the downside of that sort of approach is that it might not be appropriate to knock off an extra 25% onto all building types. In fact, that fixed approach is the methodology that was implemented in Scotland's Section 6 sort of calculation method, where we're now at a point where, in order to meet the current Section 6 regulations, you're looking at knocking off about 50% of the energy consumption compared to your notional building. And there really isn't any guidance as to where should that savings be made. It's a huge chunk of energy just to try and shed. And in a lot of buildings, perhaps something like a hospital, where there's not most of the energy consumption is attributed to things like sort of central plant rather than necessarily heat loss through the fabric and infiltration. It can be really difficult to shed that sort of level of energy. So in 2010, for Part L, they implemented this aggregate sort of approach. So the notional building changed quite dramatically. Now, rather than following a set of standards that would have passed 2002, we had a notional building which basically directly formed the target emission rate. So it had improved levels of air permeability, improved system efficiencies, quite tight fabric requirements, and that then directly formed the target emissions rate. Now, I think the main disadvantage of that approach was, while it was being implemented, designers really didn't have a good feel for whereabouts their target emission rate was going to lie until the software tools were ready and the approach was out. Now, the 25% aggregate figure was a value that was sort of given out prior to the regulations becoming active. But a lot of our feedback from our clients indicated that the sorts of reductions they're seeing are in many cases much greater than the 25%, often up towards a sort of 50% sort of range. And I think that was something that took a lot of consultants by surprise, just quite how tough the 2010 regulations were going to be. Now, one of the things I see as an advantage of this sort of aggregate sort of calculation method is that the notional building is set out, or it's based on a set of predefined sort of settings. So you've got a predefined sort of fabric setting, you've got sort of system efficiency parameters, you've got sort of air permeability sort of parameters. So if you can design your building to match those properties, you should have a compliant building. If you're to build the notional building, that building would comply. So it gives users sort of a template. These are the sorts of areas where if I'm doing poorer than the notional building, I'm going to have to make up that savings of elsewhere. So it really quite often, whenever I'm offering sort of guidance to either designers or to clients, I'll sort of point out, well, this is where your building is currently poorer than the notional building. So these will be areas to focus on. You want to bring that into line with your notional building, and you'll have a much easier job in sort of meeting compliance. Now, one of the things that's worth noting is that a lot of the specifications for the notional building are a lot better than things like the Criterion 2 limiting values. Criterion 2 is really set as the backstop sort of levels. You must have, at the very minimum, this insulation level, or this system efficiency, this lighting efficacy. But a lot of the time, those are the figures that perhaps designers at the very concept stages will be using as this sort of specification. Will be better than that, but perhaps not much better. Now, for example, the fabric requirements for the 2010 notional building, I believe for walls U values, for example, are down at 0.26. Your Criterion 2 is up at 0.35. So what I often come across is that designs will come in where perhaps walls have been built maybe to slightly better than Criterion 2 standards, but the building's already on a back foot. The loads being placed on it are already worse than that of the notional building, meaning that it needs to make up that savings of elsewhere. Now, my colleague Neil sort of said earlier that we've always had this sort of safety net of applying renewables to that, and that's often the case. That the design will get so far down the line without, I guess, addressing the areas where they could have improved upon the fabric or the form or the overall performance of the building, and are left so far down the design that it's too late to make some of these changes that could have been addressed. There's a series of reports that we can automatically export from our building, and it's one I always recommend to customers, really from the early stages of the analysis. Basically, as soon as you've got any sort of physical geometry sort of in mind, even if it's like a sort of fairly block sort of model, these sort of reports can come in useful to help advise designers. Well, this is a benchmark that you're going to be compared against. If you can again equal these parameters, you can stand a pretty good chance of having a compliant building. Now, these reports are accessed via our sort of Navigator sort of system that we offer through the software. For those of you who haven't seen our sort of Navigators before, it offers sort of a workflow to users, enabling them to basically sort of check through all the key settings or the key inputs that they would want to apply in a particular sort of project. It's also useful that as you check it off, it records when it was done, who it was by, so it acts as quite a good sort of QA as a tool as well. And you can record your own notes, so as you're entering various parameters, if you're having to make an estimate, you can record that. So you've got an overall record of the workflow for the project. Okay. Now this is one of the extracts of the report, or one of the reports I talk about. So there are two reports that can offer sort of advantages to users. One of which is sort of a key comparisons sort of input. That will check through a number of the parameters associated with the building design. So the first slide I've got in here is basically comparing the fabric and the infiltration for our proposed sort of notional buildings. Now, all of the notional building is determined from the NCM sort of modelling guide, which perhaps some of you here will be familiar with and will have read, but the majority of people will be more familiar with the actual standard, ADL2A itself. So for a lot of people, the actual parameters that the notional building aren't commonly known. We end up perhaps arbitrarily improving different aspects of their building without really much knowledge as to how that's comparing against what they're being benchmarked against. This tool is used really to try and spell that out. Now, the model I've generated this from has been sort of modelled based on the 2013 sort of notional building sort of standard. So all of my performance attributes are better in my actual building than in the notional building. But what we would see is that the report would automatically highlight any areas of performance where the notional building was better than your actual building. For example, if my roof insulation, the U value associated with that was poorer in my actual building, it would highlight that in red to make it recognisable to me that that's an area that I might want to focus on. Okay. After our sort of fabric, we can look at the amount of glazing within the models to see if we're going to have any issues with perhaps overheating or excessive fabric loss through the glass. So again, it highlights the area of glazing and also properties regarding the G value, if we're going to have much more solar transmittance within our actual building relative to the notional building, and if that's going to result in additional cooling loads. Okay. We can also compare the system parameters between the two. So if we have assumed given efficiencies, or if we're working to a particular set of manufacturers' efficiency parameters, again, we can directly compare those used in the notional building versus those in the actual building. Again, this will highlight any particular area where our actual building is at a back foot to the notional building. Okay. Now, as you see some of the efficiencies here, you can see these are, again, what's being applied in the 2010 sort of notional building, and they are really quite challenging to meet. So we've got currently a central SFP of 1.8 watts per litres per second, which includes for heat recovery effectiveness of 70% of efficiency. So again, these are the properties that are being applied in the notional building, and I think probably by today's standards, that's really quite a challenging sort of, efficiency level to try and equal. Okay. Below that, we've also got our lighting sort of parameters. So again, we can directly compare between our actual and notional buildings the lighting energy associated with the building on a space-by-space basis. Now, commonly when we get sort of, models in for support, perhaps why is my building failing, those sort of things, what we commonly find is that the lighting gains set within the building are worse than the notional, and that's perhaps for twofold reasons. Firstly, the lighting parameters set within the 2010 notional building are very efficient and very tough to try and match up with. Also, we tend to find in the design stages, it's an area that perhaps the person performing the assessment doesn't have the full information sort of on. So they perhaps don't have the full watts per metre squared per 100 lux of levels. So they'll assume perhaps a fairly conservative sort of estimate. Now, I find this sort of output useful because it means that whoever's performing the compliance assessment can go to their electrical engineer with this information. Say, well, these are the values that are being applied within our notional. These are the targets we really want to be trying to hit, and they can then advise whether that's going to be possible. Or at least it gives them like an indication as to what, let's see, whether it's going to be sort of practical or not. Also, we've got in the end section a set of controls. So in the 2010 notional building, we started implementing photoelectric controls into probably the majority of activity types within any perimeter spaces within the building. So again, we're now in a position under 2010 methodology where just to equal the notional building, not only have we got to have very efficient sort of lighting fittings in place, but we've also got to have photoelectric dimming controls in them, and that's again just to keep up with the notional building. So really across the whole range of the notional building's performance, basically whether it's the fabric settings, infiltration, system efficiencies and controls, we really need to be sort of designing to a very high level, again, just to match up with this. Anywhere where we fall behind that, and we're needing to make up that deficit sort of elsewhere. And that's often where, I say, the crash net of renewables sort of comes. And designers will get towards the end of the project, they'll find that there's little scope for making changes, and they're perhaps forced to putting in some PVs or sort of wind turbines in order to bring their target emission rate down, or their building emission rate down to a compliant level. And these are all outputs that the users can get as soon as they have any sort of geometry sort of available. So really from the concept stages of the analysis, the architects can say, well, these are rather than using the criterion 2 U values as my specification, these U values here, these are really what I should be trying to hit, or perhaps even improve upon them. Okay. The second report, which we can output from the VE, is aimed after you've performed an energy assessment. Tend to be sort of accessed a little bit further down the line once you've populated your model with your lighting powers, your and so on. Now, what this report does is really summarises many of the key outputs from the Vista report. Now, within Vista, users can access their building performance and they can interrogate their model at every time step to really get a good understanding as to what's happening. What this report does is really collates and summarises that information. On the left-hand side, we can see a chart, which is essentially sort of breaking down our actual notional building results into carbon emissions associated with them. And it means we can directly compare or directly visualise, well, what are the most dominant carbon emissions within a design, whether it's heating, auxiliary energy, lighting, cooling, domestic hot water. Now, depending on what's the most dominant, that then gives the user sort of the information required to most effectively reduce the target emission rate of their building. For example, in this case here, I can see that domestic hot water is the least, or has the lowest sort of carbon emissions associated with the building. So if I was wanting to improve this building further, probably putting in some solar hot water collectors wouldn't be a very good sort of use of investment. Because I know, fair enough, it's going to reduce my domestic hot water, but it's only addressing really a very small part of my overall energy consumption. Now I can see that probably lighting is the biggest carbon consumer in my design. So that's probably one of the areas I'd want to tackle first of all. I would want to perhaps look at improved controls, perhaps whether I can, if I've not already implemented photoelectric or occupancy sensing, see if I could introduce those into the design, or see if I can perhaps look at alternative technologies for luminaires. See if there's something more efficient that I could use to help drive that down. Now, what we can also say, as well as looking at the overall sort of carbon emissions, we get a direct comparison between where the notional building is and where the and where our actual building is. So again, after the analysis, we can again highlight areas where the notional building is outperforming sort of our actual building, which again would probably indicate that there's scope within that region to make further improvements that will help me get closer to my target emission rate. So in this particular analysis I've run, I can see my domestic hot water and my cooling is poorer in my actual building than it is in the notional building. So those would again perhaps be areas I'd want to investigate. Well, why am I performing poorer? And then sort of go and make changes to try and to bring that at least sort of into line with the notional building. Now, I guess the whole advantage of having this sort of approach for compliance, where we've got limiting values, isn't to fix users in to say, well, you must have these U values or you must equal the notional building. It's to give sort of flexibility. But I think the values at the notional building should at least form an informed specification really as to where people want to start off their design, rather than have to try and make up the deficit elsewhere. Now, while at the moment it's possible, if you're not building quite to these standards, there is scope in some places. For example, improved controls with demand-controlled ventilation or occupancy sensing that helps you get some credit back against the notional building. A lot of those areas are disappearing in the 2013 regs. So again, you've got less space to try and claw back any energy savings that you might have had under 2010. Okay. So going back to this report, this report's fairly dynamic. It will automatically interrogate your results and it will feed back sort of recommendations to you. The recommendations that it gives are sort of tailored based on the results set. So it'll automatically sort of structure the elements or the end uses based on which are the more dominant. Then the recommendations are based not only on what are the dominant issues, but what's contributing to that to that overall loss. For example, here it gives me a more detailed breakdown of my heating carbon emissions. On the right-hand side, it then explains, well, these are your fabric losses, these are your infiltration losses. So probably if you're wanting to reduce your heating load further, you're best to start tackling the insulation levels. Okay. Right. So moving on to 2013. I said the 2013 sort of regulations from what I've seen so far, at least with regards to criterion 1, do seem to follow much the same sort of approach as 2010. The target emission rate will be based directly on the notional building, and it will be, again, there will be a specification for that notional building that, that we would need to equal or be better than in order to demonstrate compliance. Now, the original plan, I think the government's preferred option, would be to have an aggregate reduction of 20% below the current 2010 sort of levels. Okay. I think there's perhaps been a bit of resistance within industry. So within the current consultation, there's also a notional specification for just an 11% sort of reduction. So I think that it's still going to be debated which of these options will be sought in the 2013 sort of regulations. Okay. But the consultation was only published fairly recently, so it was just towards the end of January, and it's going to close sort of later on in this month. Okay. Now I'll talk about some of the differences that we have in the 2013 sort of notional building. Now, one of the key differences is that rather than just having one specification for the notional building, we've got two. And that really depends on whether the building is going to have heating only or whether it's going to be air conditioned. Now, from what I've seen so far, the parameters associated with the notional building in a heated only building look much stricter and much tougher to try and match than if it was an air conditioned building. Now, once I've talked a little bit about the changes to that notional building specification, I've also got a case study which just goes through a sample building illustrating the sorts of energy reductions that we're actually seeing. Okay. So, in the notional building for 2013, you can see I've highlighted in red any elements that have changed from 2010. So, a lot of the U values are now really quite low. And again, we'd probably be looking to try and match those within our design. The two that stand out, well, all of them stand out quite a bit. I think probably in particular, sort of roof U values of 0.1 watts per metre squared Kelvin, and glazing sort of dropping to 1.4 watts per metre squared Kelvin. I'm not sure if 1.4 is really going to even be achievable still with double glazing, or if it is going to require perhaps a shift up to triple glazing. But I think either way, that's going to be these specifications are going to be quite onerous targets to try and hit. If, however, the building is air conditioned, you'll see that notional building U values haven't changed at all. They're still the same as they are in 2010. And just for comparison, I've also put in the criterion 2 limits. So again, we can see that the limits set out with regards to design flexibility are across the board much higher than what we're being benchmarked against. Okay. Now, it should be worth noting those are the criterion 2 limits for the 2006 and 2010 regulations. I've not seen any information yet as to whether those will be changing in 2013 or if those sort of backstop values will remain the same. Okay.
How do they define air conditioned? Has it got to be fully mechanically ventilated, or can it be naturally ventilated and you just add air conditioning?
I believe it's anything with cooling is their definition.
People are just going to buy it. I mean,
well, that's precisely my concern about it. That building, well, what I can see happening if this if it goes forward with the parameters in this consultation, is that people would have, the building perhaps only needs to have heating, will have perhaps split systems put into it. So the notional building would qualify under the air-conditioned sort of option, making it a much easier target to try and hit.
Do you know what the thinking is behind the higher U values for your
I don't know for sure. What I would expect is that if the building is going to be sort of dominantly heated, it perhaps makes sense to have it better insulated than a building where cooling is going to be dominant. I imagine if you were working in an office block in London, for example, where you've got sort of warmer climate, high internal gains, and overall a greater cooling load, then if you were to insulate that to a higher level, then you're going to be trapping a lot of that heat in and increasing the cooling load further. So from a design point of view, I can see the advantage of having, or why you might want to have poorer U or better U values in areas where you've got sort of a dominant heating load. But I think when this is going to be applied to when designers are faced, well, if I go for this system versus that one, I've got a much easier target. I can always guarantee which direction they're going to go. As I said, the paper's in sort of consultation at the moment, but this was one of the areas that I found perhaps of most concern. Because I think if we do see more buildings becoming sort of air-conditioned, while they might achieve the compliance easier, I expect we would see sort of a net increase in carbon emissions across the building stock, which obviously isn't the intention. So compounding that, when we look at air permeability for the 2013 specs, we've got a notional air permeability of just 3 cubic metres per metre squared at Pascal, versus 5 in the air-conditioned as it currently stands. Again, I think in practical terms, I think hitting 3 is going to be extremely challenging in the majority of cases. And it will only really be through an actual air pressure test that it can be determined whether or not that's been hit. And if, come the end of the design, designers find they haven't actually been able to attain that level, they could be on the back foot of trying to find out where the further energy savings can be made. So I think that sort of target is be incredibly difficult for designers to try and design to, and again, it's sort of compounding the issues we saw with the fabric, where if you've got a heated-only building, you've got a much harder target to try and hit. Okay. Next, we've got the system efficiencies. So they mostly have stayed the same. We've got a slight increase in the heating efficiency, up from about 88% to about 91%. At least that's how I've interpreted the consultation document so far. I think some figures include for delivery losses, other ones don't, but that's my understanding of it. Cooling and sort of ventilation and heat recovery elements all remain the same across the board, regardless of whether it's air-conditioned or heated. However, things like our fan power units for fan coil systems, the Notional building would now have a lower terminal unit SFP than it would under 2010. So in the current regulations, we've got like a fan coil terminal unit of 0.5, which, as I understand, it's probably fairly industry standard. Now, I've put a star next to this. This 0.3 is really based on the 20% aggregate reduction option. If we were to look at the 11% aggregate, we'd be looking at 0.4 for that terminal unit. Okay, but I think if we do go with the government's preferred option, 0.3 to me seems like really quite a tough target again to hit. I think it's really again pushing the highest end sort of specification for manufacturer's plant that's available today. And I think what's probably the biggest sort of change is the photovoltaics at the bottom. In the 2013 regulations, again, based on the 20% reduction, the Notional building will include PVs within the model. So again, where you could have previously had renewables as some sort of safety net, again, now you're looking at including them just to keep up with the Notional building. Now, the area of PV that would be applied is, as I said, there's a 1.6% of the gross floor area of the building, but limited to 50% of the available sort of roof area. Okay, but I don't imagine that roof area limitation really come in unless it was quite a high-rise building that you're looking at, maybe 25 stories sort of or more. But there would be a fairly significant cost associated with installing that level of PVs, and it's from this case studies I've looked at so far, it's not an insignificant reduction that applies to that Notional building.
Why PV? Just because it's bolt-on?
Good question. It's I expect so. I think the calculation for the Notional building is fairly sort of straightforward. They're assuming that it'll have 120 kilowatt hours of electrical generation per metre squared of PVs sort of in that model. Whereas I guess within our sort of simulation, we would typically sort of include or do a much more detailed sort of assessment on that. So we're taking into account the weather analysis, solar positions of your PV relative to the sun, and so on.
Is 120 viable in Newcastle?
I've not done that check yet. I'm not too sure. It's yeah, it'd be interesting again whether the sort of the electrical generation figures that they're discussing at the moment are actually sort of feasible. Again, that option is currently just falling under the 20% aggregate. The 11% doesn't include for any renewables. So I think it will be interesting to see which side of the fence the consultation paper ends up sort of falling on. I think if it's certainly the 20%, it's going to mean a lot of big changes for designers, and a lot of these sort of parameters will really be considered from the outset. Sort of moving on to system controls. Now, system controls used to be an area, well, at least in the 2010 sort of methodology, where the users could claw back a lot of the energy savings, largely because they weren't included sort of in the notional building. Now, already in 2010, for things like pump controls, the notional building was already using the highest specification of pump controls available, so there wasn't really any scope to improve upon it. And that's remained the same. The biggest change is with demand-controlled ventilation. It's where the 2013 model will include for demand-controlled ventilation, CO2 sensors and speed control, effectively offering the greatest level of reduction both in ventilation supply and auxiliary energy than the calculation methodology allows. So again, there's no scope really within the designers to improve upon that. They could really only equal the settings that are being applied. Okay, moving on to lighting and lighting controls. And as I mentioned earlier, in 2010, a lot of users found it really difficult to match the lighting levels within the lighting power consumption within their actual design, because the notional building was already a very tough target. It was set at 55 lumens, or luminaire lumens per circuit watt, which is going to be which will increase to 65. So it's again a sizable jump upwards, where the designers will need to again try and meet that. As I said, 2010 for daylight control, the notional building already included that in a majority of space types. So things like classrooms, office spaces, meeting rooms would generally sort of include for daylighting control. Other more transient spaces didn't typically have it. What's changed though is that occupancy sensing is now also included within the notional building. Occupancy sensing was again an area where designers could install it within their actual design, and it was an easy way for them to claw back some energy. And because lighting makes up such a dominant part of the overall carbon sort of picture, it was a fairly significant sort of saving. Now again, it's included as standard in the notional building, and again it's set at the option that gives the greatest overall reduction. So again, there's really not much scope to reduce the lighting power sort of further within your actual design than it is in the notional. Okay, now, based on the specification we've had for the notional building, I've performed a fairly quick sort of case study just to try and comprehend, well, what sort of reductions can we actually expect. As I mentioned, when 2010 regulations first came out, we were given the indication that there would be an aggregate reduction of 25%. But when the calculation tools and the methodology were finally released, often people were finding it to be much greater than that sort of level. I was also intrigued because, as we've sort of pointed out, we've got this different specification for heated buildings and for air-conditioned buildings. So I wanted to see what sort of difference we were seeing in the overall reduction in those two sort of test cases. So the case study I've based my analysis on was one of the accreditation models required that we produce for when we're submitting our software. So this is one which had been previously tested to quite a large degree of detail. I used this model because it was deliberately set up to match the 2010 notional building. So the results for our building emission rate exactly matched our target emission rate. What I was able to do here was just change my actual building to then match the specification for 2013. So I could then say, well, for the same building, what sort of reduction in target emission rate are we seeing? Okay, So this is I've done 4 models I've done 4 case studies in total, both for the 11% reduction specification and the 20% reduction specification, both for heating only and air conditioned models. So those are the 4 permutations that we've looked at. So the chart here indicates the carbon, for this particular sort of case study, the CO2 emissions on a kilograms per metre squared basis for a 2010 notional building versus a 2013 notional building. Now, this is based on heating only, so it was natural ventilation with radiators, and based on the 2013 11% reduction specification. So the target for this would have been, or the expectation perhaps going into this, is that we would be observing a carbon emissions rate 11% lower than it was in 2010. What we're actually seeing from this case study is it's closer to 28% lower. And so straight away a much greater reduction than perhaps industry is expecting. The next option was, again, the same heating-only sort of a set of analyses, this time based on the 20% reduction specification, heating only. We're seeing a 33% sort of reduction. So again, a much greater sort of difference between what we might have been expecting versus what we're seeing. Now, I want to stress that this is just a case study, and it's based on the aggregate reduction. But what the sort of results I'm seeing isn't out of line with what I was expecting. That the sort of reduction we're seeing is going to be greater than that, particularly in the heating only, simply because of the fairly significant changes in the building fabric. Okay. The next set of results are based on the same building, but this time with a fan coil system in place, using the 11% reduction specification for the 2013 model. What we're actually seeing is perhaps a bit more encouraging. We're seeing that for an air-conditioned buildings, the sort of reduction, again, this particular case study's reporting, is about 11% when benchmarked against a 2010 model. So it's a little bit greater, but not discouragingly so. It's still in the same sort of again, given that different building types will see different levels of reduction, I think it's fairly encouraging that the air-conditioned specification is going to give the right sort of ballpark to what would be expected. And then lastly, we've got our 20% reduction specification for air-conditioned. So again, the same building, just with a different 2013 spec. And we're seeing a 22% reduction when we might have expected a 20%. Again, very encouraging that I think the sorts of target emission rates that we'll see are broadly in line with the expected reductions. Okay, so sort of conclusions from that sort of case study is that it supports the hypothesis that if you've got a heated-only building, it will be tougher to demonstrate compliance compared to if you have an air-conditioned sort of building. Which I think when we were looking at the sort of the specification for that building was pretty much a no-brainer. But I think that's a fairly conclusive proof. As mentioned, if it's an air-conditioned building, the reduction in target emissions from case studies so far do seem supportive that the anticipated reduction levels do seem fairly consistent with what we're predicting. However, in heating only, it does appear that the target emission rates will drop by a much more significant margin than perhaps the 11% and 20% sort of values suggest. Okay. Now, I guess my main concern sort of over this, I think as we discussed earlier, is that if it's demonstrated that it's easier to pass with an air-conditioned building, that this may be the approach that designers take. So buildings that could have been, that don't require cooling, will have it installed simply to have an easier notional building and a simpler pass. As I mentioned earlier, the consultation paper is still into consultation. So it's not to say that these specifications will be what finally get put through, but I think that's something that would perhaps be of concern currently. I'll move on to the FAQs. I think this is really sort of covering a lot of the fairly typical questions that we get in through technical support from various users. So I've highlighted about 3 or 4 areas which commonly cause concern or have issues with customers. I'll try and move through these fairly quickly. Now, Now, the first query, I want to address is really on auxiliary energy, as this is an element that changed considerably in the sort of a setup between the 2006 methodology and 2010 methodology. Well, in 2006 there wasn't really any published sort of method. The auxiliary energy figure was up to the user to enter what they felt was appropriate, which led to a large variety of figures being used, and also the energy assessor didn't really have any means or any requirement to justify the figures that they were using. Now that changed in 2010, where a specific auxiliary energy methodology was put into place, which would then calculate your building's auxiliary energy. Now that was broken down into 4 different types, which are indicated in this table here by the different equations that are being used. So on the left-hand side, we've got all the different NCM system types that incorporate fans, and the equation that they relate to. Now, I think generally on the whole, the methodology that they've implemented has improved consistency, so we're getting more realistic sort of figures out, and at least there's a methodology there for people to follow. But I think it does have a couple of inherent flaws within it. Essentially, any system that falls under equation 9 will determine the same auxiliary energy as any other system in it. So the approach that's in the current auxiliary energy methodology doesn't differentiate between a VAV system or a CAV system, where you would expect to see really quite enormous differences in energy consumption. So I think that's one of the overall flaws sort of in the methodology that's spelt out in the current sort of NCM modelling guide. So I'm hopeful that that's going to be something that will be addressed in the upcoming regulations. This is in that table is extracted from the NCM modelling guide. That's right. So just to give an indication as to what these different equations sort of represent, again, this is from directly from the modelling guide. So the equations up in the top here relate back to the different system types. So system 8, that's typically the system that will be employed within the notional building most of the time, and it generates probably one of the lowest levels of auxiliary energy. The calculation is based on this FAR max times SFP central. Now, simply put, FAR max is your outside air requirement, so basically your minimum fresh air, multiplied by the specific fan power of the central plant, which is at 1.8 in the notional building. Then, in addition to that, we've got a local fan. So it's essentially performing like a fan coil system. We've got this SCR value. Now, this is calculated based on the peak heating or cooling loads within the space. So it's essentially calculated to meet the peak heating or cooling load based upon an 8-degree delta T between the supplier temperature and the room temperature. This was something that was just introduced in the 2010 methodology, which I think makes a lot of sense. Prior to that, you could have rooms with completely different loads that happen to have the same system type, and they would both calculate the same auxiliary energy. Now, when you've got the same system type applied to them, they've got different loads associated with them, you'll get different auxiliary energy values. So the logic behind it is fairly simplistic, but I think it gives a better representation than what we had before. So we'll see the majority of the airflow within the design is taking place locally, and it's going to be using the terminal SFP, which is going to be a good bit lower than that of the central plant. Okay, I think that's it. Now, equation 9, that's really sort of representative of our central-based plants. So again, we've got our minimum fresh air being introduced to the system. We've got recirculation, but it's happening at that local plant. So the fan power associated with it is typically much greater, simply because the SFPs of our central plant are going to be much greater than that of any sort of local-based systems. So generally, if you were to opt for a system type that uses equation 9, auxiliary energy in your actual building is going to be a good bit higher than that in the notional building. I guess the advantage of having your central system is you've got the ability to capitalise on free cooling. So you can, if you're able to increase the amount of outside air that can be introduced, that can offset the mechanical cooling loads within your designs. So while I'd expect equation 9 to always result in more auxiliary energy than equation 8, There are occasions when the net energy can be lower, just simply due to the reductions from free cooling. Again, what I think is the main limitation of using that equation is that it doesn't accurately differentiate between sort of constant air volumes and variable air volume systems. I expect you'd see a much greater level of reduction in that case. Equation 10, it's a bit of an odd one, but it's generally used for things like your active chill beams and, let's see, what was the other one? Your sort of induction sort of systems. It behaves much in the same way as equation 9, but it's reducing the calculated sort of volume airflow rate. Lastly, equation 11. That's typically used for your hydronic-based systems, so your things like your displacement ventilation with sort of chilled ceilings. So the only fan power associated with it is really our outside fresh air multiplied by our central SFPs. So it's essentially the same as equation 8, but without the terminal unit sort of employed within it. Okay, so it's that's just a breakdown as to, I guess, what an illustrative sort of breakdown of this, so what the different system types are essentially doing and how they're being calculated. In addition to this, we'll also have pump power that gets added on, and that's simply taken from a table that's in the NCM modelling guide and varies depending on the types of controls, whether you've got multiple pressure sensors in it or not, or I think there's about 3 or 4 different VAV sort of pump configurations, and also whether the building has heating only or heating and cooling. But that's just a fixed value that gets employed. And also it's worth noting that the value the notional building uses is again the top level of specification that you can select. So again, there's not really any scope to improve upon the notional building settings. Okay, the main comment we have from users is that their auxiliary energy is much greater than that in the notional building. Most of the time it's because they've gone for a central plant that's using equation 9. Okay, briefly want to talk about sort of the mechanical ventilation setup. An area that causes quite a lot of confusion is basically why there are multiple areas in the software for defining the SFPs. Or sometimes it's at the system level, sometimes at the room level, and I think there's a lot of confusion regarding that. Now, generally, whenever the system is providing the main space conditioning, so if it's a VAV, constant air volume, something using, I guess, equation 9 that we talked about, the specific fan power will be set at the system level. So within the Apache Systems sort of dialog, the user can enter their SFP sort of within it. So there'll be a sort of screenshot just down there of where they would set that. For mechanically ventilated systems where the supplier isn't doing the main conditioning, it might be tempered or it might have sort of heat recovery included in it, but it'll generally have some other source of heating such as radiators or split system, then the SFPs are set at the room level. So that's set under room query, or it can be done throughout the building through edit group attributes. Okay. Okay. Now, moving on from that, another area, before I move on, I think probably one of the exceptions to that rule is when you're dealing with a fan coil system. It's got 2 different fan parameters that you need to enter. Firstly, you've got your central sort of SFP for your main supply, supplying the outside sort of air, but you've also got your terminal unit sort of SFP. So in the case of a fan coil system, you'd have the 2 options available to you. So you'd have your central SFP entered at your system level, and your terminal unit SFP entered at the room level. Okay. Now, again, moving on from that, I think what again causes quite a lot of confusion for users is where they've got the option here of setting at the local level mechanical supply and mechanical exhaust. Now, the non-domestic building services non-domestic building services guide stipulates that the specific fan power should be calculated by taking the total power consumption of both the supply and extract fans and dividing that by the supply sort of airflow sort of rate to the space. So that's effectively what should be entered on our box on the left-hand side. So it's the aggregated sort of SFP. Now, I think what causes some confusion is we've got the option for mechanical exhaust. And what I've seen in the past is users splitting up their supply and extract, so that they've got their supply fan SFP on the left-hand side and their extract fan SFP on the right-hand side. Now, really, that exhaust option is really reserved for things like toilets, changing rooms, kitchens, where it's really sort of ventilation in addition to the fresh air requirements. Now, when we've got a mechanical exhaust, we can specify the airflow rates that are attributed to it, and also the specific fan powers associated with it. Now, mechanical supply will be equal in both the notional building and the actual building, and based on the NCM activity database, whereas with our exhaust, the notional building will adopt whatever airflow rate the users enter. So it's essentially matching what's in the actual design. The difference would be that the supply fan power, or the specific fan power for mechanical exhaust would be fixed to a notional level. So that may not be the same as your actual design. Okay. A common query that we get is that the domestic hot water loads are higher in their actual building than in their notional building. I'm betting you've got a question on this. As we mentioned earlier, a lot of the templates are driven, many of the template types are driven quite heavily by domestic hot water demand. Buildings like hotels, sports facilities often have a very high hot water consumption associated with them. Now, it's been noted that the efficiency values that the notional building use are extremely onerous, and would be pretty much near impossible to actually try and meet in an actual design. The notional building only allows 5% from the domestic hot water system to account for storage losses, secondary circulation losses, and so on. To put that into context, in the previous notional building from 2006, the losses accounted for about 45% of the overall reduction. So it's an enormous jump from where it was. To get the sort of efficiency levels that are being employed in the notional building, you'd probably be looking at an instantaneous point of use sort of gas-fired DHW heater, which is just not going to be practical in so many sort of applications. So that's an area that a lot of our customers, where they've got a DHW dominant sort of building, are really struggling to try and match those same sort of levels. Now, one thing that you can do is just check through the settings that have been applied to your model. If you've opted for a lot of the defaults, where the information is unknown, the defaults will often be quite cautious. So there's a good chance you'll be able to get losses or DHW losses that are a lot lower than the default settings would necessarily allow for. So that's the first case to check into. Secondly, ensure that you've not associated domestic DHW losses with multiple system types. We'll quite frequently see a user will create one system, which is maybe doing their whole building. They'll set up their DHW settings with it, and then they'll copy that system multiple times over. So they're also essentially copying those same losses multiple times over, which can stack up. Okay. And I think for the majority of building types, domestic hot water makes up such a small fraction of the overall energy that while it's difficult to match the notional building, the saving can be made elsewhere to make up that difference. But I say there are a lot of building types where because it's a dominant load, it's just really, really difficult to get anywhere close to matching it. Okay, and lastly, results changing after software updates. Now, although regulations were, regulations were released, October 2010, there have been frequent updates to things like the calculation methodologies, the NCM activity databases. Let's see what else has changed. The EPC lodgement procedures. So every time there's a change like that, we also need to release an update to our software that incorporates those changes. Now, that's not necessarily a problem for things like your Part L projects. If you start a Part L project using one version of the software, you're quite within your rights to use that same version the whole way through to completion. So you don't really have any surprises with changing activity types and so on. It's a bit different for EPCs, however. EPCs need to be lodged using the most recent version of the software. So if you were to perform an analysis at the early stages of your design and get say, call it a B rating, particularly if it's around the borderline between, let's say, a B and a C. It's not necessarily to say that come to completion, if there's little being changed within the design, that it will still be a B rating come the time when you come to lodge it. So it's something to be aware of.